All right. So up to this point, every function that we've seen has been pretty nice. I mean, in other words, I've been pretty picky about what it is that we're trying to graph. We're going to try something a little bit different now. And what it's going to do is it's going to change our process just slightly. You know, we have this process, and it's going to change a little bit. So let's take a look here at this. F of x equals 2x to the fifth minus 11x to the fourth. Do we need to change the lighting in here at all? Yes? Okay. We'll crack the windows and... yeah, that's even too dark for me. Yeah, can y'all just crack those a little bit? Just pull that, just so we get a little bit of light coming across here. Whoa, okay. That okay? Everyone good? All right. I want to make sure my audio is recording because it sucks to have to... yeah, that looks like it's okay. Bah. Bah. Okay, so everything here is... I mean, that looks like a polynomial, right? I mean, it's what we've done in the past. The biggest issue that's different today now is this 2 in front. If you look back at every problem I've done up to this point, the leading coefficient has always been 1. Right? It's always been 1. This is the first problem where the leading coefficient is something other than 1. And if you remember on AC method, when you were learning to factor AC method, they gave you like 2 techniques. One, or they always said if the number in front of x squared is 1, then it's easy. If it's something other than 1, it's a little harder. It's kind of like the same thing here. So just pay attention. That's the big difference right now. And let's go through now the steps. The first thing would be to identify the left and right hand behavior. So what's my degree? It's 5. And that is an odd number, right? And then my leading coefficient is 2. That's greater than 0. It's a positive number. And therefore, the left side will go down and the right side will go up. And in the middle, I'll have to figure that out. So no real difference there, right? The second step was to find the X intercepts. And for the X intercepts, we take the entire function, we set it equal to 0. And what can we do with that? Factor how? Grouping probably won't work, but yeah, GCF always first, right? Try and get GCF, which we do have something common to all of them, right? X squared. I can almost promise you something like that on the test. Promise. Because I always want to make sure that you can pull the GCF out and then not forget it later. Because later on, after you've done all this stuff, you have to remember you had that x squared way up at the beginning. Okay, now what's in the parentheses here needs to be factored. And it will not work with grouping. All right, grouping will fail. So what we did last time is we came up with this list of numbers, didn't we? And that list was based upon which number? 36. Okay, I want you to do the same thing. Let's make a list off of the numbers from 36 first. That's not going to change. So here's my list. All the numbers that multiply, or I'm sorry, that divide into 36 or multiply to be 36. 1 and 36, right? 2 and 18. 3 and 12. 4 and 9. Anything else? 6 and 6. So all you have to do is put 6. You don't have to put 2 6s next to each other. That's it, right? So that's not different. That's not different, right? Here's the difference. Now what you have to do is look at the number in front of that x cubed, right? In the parentheses right there. That didn't really look very good. This 2 right here. Before it was a 1, right? So we didn't care about it. We didn't care. Now what we have to do is look at the 2 and make a list just like we did with the 36. What are all the numbers that multiply to be 2? Just 1 and 2. So I'm going to put that list below the list I just had. 1 and 2. So now we have, I'm going to say this first list, I'm going to call that list, I'll call it list A, and the other one is list B. So far, okay? Now, this is the tricky part. What we're going to do is we're going to create from this, those 2 lists, a final list. You do not have to do any of this if that number is a 1. All right? If the number is a 1, you just do what you did for your homework and everything else and what we've been doing in class. But if that number is something other than 1, you must do this part, final list. Now, what this final list is the confusing part. What you're going to do is you're going to take every number in your list A. So 1, plus or minus 1, plus or minus 2, plus or minus. You're going to take each of those numbers, right? Each one. And divide it by each number in the other list. So see all the ones I circled? I need to take all of those and divide them by the first number in list B, which is just a 1, isn't it? So isn't that just the same list? Okay, so let's write that out first. All those numbers divided by 1 give you the same numbers. So my final list will actually be, yeah, you ignore the signs because positive, negative, when you divide every combination, you still get positive, negative. All right, those are all the original list A divided by 1. Do you see that? But do you see why when it was a 1 out there, you didn't need this step? Because you were going to divide it by 1 anyway, and it was going to be the same thing. Okay, now I have to go through and divide all those numbers this time by 2. So I need to go through and take every number I had in my original list, my list A, and now divide each of them by 2. All right? So let's take the first one. What's 1 divided by 2? Plus or minus a half. So I'm going to add that to the list. I'll just put it below here. Plus or minus a half. Then do the next one. What's 2 divided by 2? It's 1. Do I already have 1 in my list? Yeah, so I do not have to rewrite it. Now take 3 over 2. That's not in my list, so I need that one. Plus or minus 3 over 2. Next. 2. Do I have 2 in my list? Got it. 6 divided by 2? 3, I've got that. 9 divided by 2? I do not have that, so I need to put that in my list. All right. Let's see, what's next? 12 divided by 2? 6, I've got that in my list. 18 divided by 2? 9, I've got that. 36 divided by 2? 18, I've got that. So really, it only created 3 new possible, well, that's, I say 3. This is actually 6 different numbers, isn't it? Positive and negative. Make sense? Now, that's our final list right there. We're done. Any questions on that difference, that slight tweaking of what we did from last time? Now, the question for you is going to be, okay, you're going to start with your synthetic division box now, right? Where do you start? We're going to stay the same. Go with the lowest number, but don't do the fractions. Wait on the fractions, okay? If every other number in your list doesn't work, go to the fractions. The fractions are the hardest ones to do. So I say avoid them. And on a test, I've already promised you it's going to happen within the first few tries if you do it the way I said. Start with the smallest numbers. Wait, put the fractions at the end. All right? So let's try some synthetic division here. I'll just make my synthetic division box. Oh, no, you're going to use a 2. Yep. Well, I'm taking all the numbers. I'm looking at the yellow part, right? That's what I'm trying to factor. What's the number in front of x cubed? 2. So that's the first number in my synthetic division box. It won't be a 1 this time. And then negative 11, then negative 12, then 36. Now, would you like me to show you the numbers that don't work, or do you want me to just get to the one that does? Just get to the one that works? Okay. 1 will not work. Negative 1 will not work. 2 will not work, but negative 2 will. So it would have happened on your 4th attempt, on your 4th try. So let's do negative 2 out here. Let's see, 2 comes straight down. Negative 2 times positive 2 is negative 4. When you add that straight down, you get negative 15. Multiply negative 2 times negative 15 gives you positive 30. Add down, you get 18. Multiply negative 2 times 18, you get negative 36. And you get a remainder of 0, which is what we needed. Now what this turns into is an x plus 2, right? And then 2x what? Squared, right? Minus 15x plus 18. And the 2x squared minus 15x plus 18 is a quadratic, isn't it? And I told you already, as soon as you get to a quadratic, I would expect that you can somehow break that down. Now, I'm actually going to show this one because this one's a little bit, not complicated, but it's not just a basic old, guess and check or AC method. So I'm gonna do this one. I'm going to do AC method. I'm going to do 2 times 18, which gives me 36, and then negative 15. So I need to come up with 2 numbers that multiply to be 36 but add up to be negative 15. Dun, dun, dun. Negative 12, negative 3. So again, that might take you some time to figure that out, right? But that would be it. Now, I think I'll do my work on the side here. I'm showing this AC method. And I'm going to do the AC method with grouping. So the way you do this is you rewrite the negative 15x, that's the middle term, you rewrite it using the 2 numbers you just found. So instead of negative 15x, I write negative 12x minus 3x, then the plus 18. And now this should go by grouping. What can I pull out of the first 2 terms there? 2x. So I pull a 2x out. I'm left with x minus 6. And what can I pull out of the second group? Negative 3, and I'm left with x minus 6 again. And they match. The x minus 6 and x minus 6, that's what you need. So this turns into x minus 6 times 2x minus 3. Questions on that? Okay, let me bring that back over here to the left side. I had the x plus 2. Next to it, I have this x minus 6, 2x minus 3. So this, what I just got here, through my synthetic division, and then going and doing my AC method on that quadratic, represents just that yellow part from before, right? What do we still have sitting in front of all that? That x squared from way up there. Okay? So now I'm going to go to a new page and I'm going to write down where we are. We are at x squared times x plus 2 times x minus 6 times 2x minus 3. Is that right? equals 0. That's everything written out again. I want to know when all that's equal to 0. So now you set each of these equal to 0, and you get your answers. Let's see. First one, 0. Second one, -2. Third one, 6. Fourth one. You're setting 2x minus 3 equal to 0. Yep, 3 over 2. Move the 3 to the other side. Divide by 2. 3 halves, which is actually, as a decimal, it's 1.5. I'm only converting it to a decimal because I need to put it on a number line, so I want to make sure I know where it is. Tell me what I'm going to do at each of those x-intercepts. What do I do at 0? I'm going to bounce off this. Why do I bounce? Because it's squared up there, right? Even powers, you bounce. Every other one of these factors has an odd number. So I'm going to cross at all the others. That's it. Questions? I'm ready to graph. All right, I have x-intercepts at 0. At 1.5. At 6. And at -2. The heck is that? All right, so we always start by plotting the x-intercepts. What's the next thing you should do? Okay, what do you start with though? Yeah, the up left, up the left and right behavior, right? What's happening on the left, what's happening on the right. So it goes down on the left, and then it goes up on the right. So I'm going to put this going down like this and up over here. At -2, what do? Cross, so I'm going to go ahead and cross through there. At 0, I'm going to come down and bounce, right? So I'm going to come down and bounce off like this. At 1.5, I'm going to cross through, and then I'm going to cross at 6, and then come up through and be done. That's it, folks. Make sense? All right. Were there any questions on the homework? How about the bonus? No? I don't mind doing the bonus. So you can see if you got it right. Because the bonus is a really good problem. It was f of x equals x to the 4th minus 9x cubed plus 10x squared plus 36x minus 56. So now that we've gone through that other problem, the first thing you would want to make sure you look at is that number in front of your highest power of x, which in this case is a 1, isn't it? Our leading coefficient is 1, so we won't have to do those two lists and come up with a final list. All right, so first thing, left and right hand behavior. My degree is 4. And my leading coefficient is 1, which is greater than 0, so it should go up on both sides. Right? Up, up. Now the x-intercepts. So I take this thing and I set it equal to 0, and I realize pretty quickly that I can't do anything with that. This one doesn't even have a GCF, does it? I can't even pull a common factor out to begin with. This is a 4th degree polynomial, which we are going to now factor. Doesn't that get you excited?
Yes, overly excited.
I mean, you can now factor 4th degree polynomials? Wow. 56. Let's come up with our list for 56. 1 and 56. 2, 28. Does 3 go in there? No. 4? 4 and 14. 5 and, no. 6 and 7 and 8. And that's it, right? All right, now if you did this problem correctly, not correctly, but if you follow what I said and started with the smallest number and work your way up, everyone should have the same work, right? So let's see, what smallest number worked? 2? Positive 2 was the first one that worked. So let's try it. Positive 2 going into here. What are the numbers here? 1, -9. And I don't have any gaps, right? No zeros in there. Always remember if you might have gaps in there if that power doesn't appear, right? Okay, 1 comes down, 2 times 1, 2, -7. Let's see. That's going to give me -14, -4, -8. What's this? 28. And that works, right? 56, positive 56, it gives me 0. So here's what I know so far. I know this breaks down to be x minus 2, then x to the third power minus 7x squared minus 4x plus 28. Right? But the x cubed minus 7x, oh, that factors, doesn't that factors by grouping. Wow. How many of you realized that did the bonus? How many of you realized that cubic one went by grouping? Did anyone just do synthetic division again? You did, and it works, right? Okay. So I want to point that out. At this point, you could do synthetic division again on this x cubed, but it does go by grouping. So if you look at it right down the middle there, tell me what factors out of these first two terms there. X squared, and you'd be left with x minus 7. Then on the second two, you factor out a -4, and you're left with an x minus 7 again. So everything in this blue set of parentheses turns into what? X minus 7 times x squared minus 4. And then what's sitting out in front of this? X minus 2, I'll bring it down, x minus 2 again. But the x squared minus 4 is the difference of squares, right? So you can go x minus 2, x minus 7, x plus 2, x minus 2, there's my difference of squares. And then you have to notice that you have two x minus 2s. You have to see that, because your next line is x minus 2 squared x minus 7, x plus 2. That's completely factored. Now, going back to the original problem, I was supposed to set this equal to 0, wasn't I? So I'm just going to throw equal 0 on the end of this. What are my x intercepts? 2, 7. Whoa, that's not a 7. 7 and -2. What will I do at positive 2? Bounce, because the power's even. The others are odd, so cross. So my graph should look like this. X-intercept at -2. Positive 2. Positive 7. It should go up on the left, up on the right. At -2, I should cross through. At positive 2, I should bounce. So I should come up and bounce off at that x-intercept. And then at 7, come back through and cross. That's it. How many of you got that? I turned it in. Yeah? Good. The only part of that made it a bonus wasn't that this is not a problem that a lot of people think bonus is like, okay, that's beyond what I should know. I don't need that. This is a totally legitimate test question. I just had not shown you a problem where we do the synthetic once and what we have left there might require synthetic again, or in this case, went by grouping. Everything I had shown you up to this point, once we did synthetic, the thing that was left was quadratic. So we were kind of in business after that. So good if you got that. Anything else on this? Any questions, concerns? Should we write out a formal process, or are you happy with this? I mean, if we were trying to explain how to do this, how to sketch polynomial functions. If you were to be giving yourself a set of steps, the first thing you would want to do is find the left and right behavior, right? And that you use the table for, right? Use that table. The next thing you do is find your X intercepts. When you do the X intercepts, after you do that, you have to find whether or not you bounce or cross, right? And then after you do that, you graph it, right? You sketch it. I mean, those are the steps. I mean, there's a lot involved there because finding the X intercepts requires possibly synthetic division and all that stuff. Maybe you'll have to do grouping in there, AC method. There's a lot that could happen. But the overall thing is find the X intercepts and determine if you bounce across at each one. Once you've got that, you're in business. We good? On your cheat sheet for the next exam, you can have steps written out, whatever details you want to put in here, whoever you want. You just can't have worked out problems. Well, is it scheduled next Tuesday? That seems a little close. Yeah, we still have another week or so. Okay. I will give you an assignment for this, but what I think I'm going to do is after class today, after my calculus class later, I'll go back to my office and I think I'm going to email you the assignment because I have some problems that like from past tests and stuff like that I can send you so that way you have a real good idea of what I ask on tests. So I'll put that together and send it out to you today. All right, now we have done lines, we have done quadratic functions. We have now done polynomial functions. So we've done 3 of the 6. The 4th one is rational functions. And then exponential and log come after that. I told you already exponential and log are actually easier than these. Rational is the hardest. So this is it. We've made it to the most challenging of all functions to graph. Rational functions. Now, the word rational comes from the word ratio, so ratio should be making you think fractions, and in fact, that's what it is. So anytime you have a function that is equal to a polynomial, which is what we just studied, right? Polynomials, divided by another polynomial. Anytime you have a polynomial divided by another polynomial, you have then what is called a rational function. That's it. That's the definition. Now, as we're going to see, the graphs of these are they're all very different. Everything depends on what you have. Where before we had that table, right, left, right, up, down, we had like 4 possibilities. That was it for n behavior. And then in the inside, we just found X intercepts and bounce and cross, and that was it. And They all pretty much had to look kind of like a roller coaster, right? Polynomials. These don't have to all look the same. They could or could not have similar characteristics. So I'm going to start this by showing you an example of one that we can kind of hopefully get our heads around at first, and then we'll start exploring a more general approach. So our first example is the function f of x equals, I'll give you the classic example. We'll just do 1 over x. Now we have to first agree that this is a rational function. So I'll just point out the bottom is a line, isn't it? Just if you look at x by itself, if I were to ask you, hey, go graph f of x equals x, it's a line, it's linear. And the top is actually a constant function, which is also a line, right? Yes? If I say, hey, graph 1, it would just be a flat line. So we have two lines. And we talked about last class, or when we first started talking about polynomials, that all lines are polynomials, right? That lines lived in a bigger group of functions called polynomials. So we do have two polynomials being divided. So this is a rational function. Now the way we're going to graph this, just to get an idea of what's happening here, is to do it the old school style. We're going to do a big old t-table on the side here. We're just going to plug in some values of x and figure out what the function spits out. So let's start out with 1. Let's just plug 1 in. What would you get if you plug 1 into this? What's 1 over 1? 1. So if I plug in 1, it spits out 1. What happens if I plug in 2? 1 over 2. That's 1/2, right? What if I plug in 3? 1 over 3. That's just 1/3, right? Now I could get these as decimals, couldn't I? Do y'all see what I'm doing? Okay. Let's we kind of see what's happening. Let me go out to 10. How about what's if I plug in 10? 1 over 10. All right, let's go way out. How about 100? 1 over 100. Tell me what's happening to the numbers that are coming out as I plug in values of x that are bigger and bigger and bigger. The values of the function are getting smaller and smaller and smaller, aren't they? Start at 1, then 1/2, then 1/3, then 1/4, 5th, 6th, 7th, 8th, 9th. Go out to 10, 1/10, go out to 100, 1/100. What if I went out to 1,000,000? 1 over 1,000,000, right? It's a tiny number, but it's not 0, right? It's still a number. It's still some positive number. Agreed? What if I went out to, well, yeah, I was trying to think of Austin Powers and, yeah, a gajillion, zillion, whatever, right? What if I went out to there? 1 over that, super tiny number, but it's something positive, isn't it? Okay, so keep that in mind. If we're trying to think about our graph as we draw it to the right, so almost we'd be almost talking about almost like the right-hand behavior. You know, our polynomial was either up or down, wasn't it? This one, as we go out to the right, what's happening? It's getting smaller, which means it's getting closer to what? Visually, on a graph, what would it be getting closer to? Your x-axis, right? Now we'll draw it in a second, all right? But that's what's going to be happening. Let me try some negative values. What if I plug in -1? What's 1 over -1? -1. What if I plug in -2? -1/2. What if I plug in -3? -1/3. What if I plug in -10? Same concept, exactly. It's still getting smaller, but these are negative numbers, which means they start out below the x-axis and start coming up towards the x-axis, but never get there. Y'all kind of see that? Now, I think I'll start to draw a graph here. I'm going to continue my table in just a moment. I think I'll do a new page for the graph. Now, here's my graph. Let me mark out, we'll mark out 10 in each direction. 1, 2, 6. Make it 8. I can't fit 3, 4, 5. I'll just go 6 up and 6 down. That okay? Each tick mark is 1. So let's plot that first point. We plugged in 1, it spit out 1, right? So we should have a point right here, right? Okay, good. Just making sure you're paying attention. All right, out 1, up 1. It's right there. That's 1, 1. We plug in 2, it spits out 1/2. So we go to the right 2, up 1/2. We plug in 3, it spits out 1/3. Do you see what I mean by it's getting smaller? Now it's going to become impossible for us to actually put 1/10 in there and 1/100. You know, it's going to be really hard. So here's what we do. Since we see the pattern, we're going to draw this line like this. Oh man, it's not a line, it's a curve. I'm real shaky here. Oh my gosh. And it's just draw an arrow like that. Do not touch the x-axis. You can with the tip of your arrow, but man, that is terrible. And then what you need to do, I'll do it in a different color, is on the x-axis at the end, draw a dotted line like this, extending out something like that, right? Do y'all agree that's what's happening? That dotted line is telling you that at the x-axis, my function is getting closer to that value, closer to the dotted line without ever getting there. Let's go to the other side. Plug in -1, it spit out -1. Plug in -2, it spit out -1/2. -3, -1/3. So isn't that going to be pretty much the same thing on the other side? Curve going up. Come on, that's good, that's good. Yeah, I'm happy about that. Dotted line off the other edge. It's hard to draw on this because it's glass and there's no real friction between and so it's hard to keep your hand steady on that thing. I'm making excuses. It is. Makers, sorry. Makers. What is it? It's Tuesday. Yeah, Tuesday is Makers Day. All right. So that's what our graph looks like so far, right? What we don't know yet is what's happening in the middle, right? We plugged in like 1, 2, 3, 4, and we plugged in -1, -2. What we haven't seen is what happens if we plug in numbers that are between like 0 and 1, right? But the graph is missing there, so we need some more information. So let's go back to our t-table, and let's plug in some more values. Let's try a number that seems obvious that I've avoided on purpose. What number would you... 0, right? 0 seems like, hey, why didn't we just plug in 0? Well, what's wrong with plugging in 0? You get division by 0, and division by 0 is undefined. Undefined. That's critical because, look, every function we've done up to this point that we've graphed, right? Lines, parabolas, polynomial functions, all of them, we could draw them without picking up our pencil. Couldn't we? Think about a line. You can always draw the whole thing without picking up your pencil. Parabola, you could draw without picking up your pencil. The polynomials, you might bounce or something, but you could draw the whole graph without ever picking up your pencil. Rational functions might, not always, might have points in them where your graph is undefined, which means you cannot put a dot at 0. The graph will not be able to go through 0 at all. Does that kind of make sense? So right now at 0, if you go to the graph and you look at 0, you look straight up and straight down, we should have no graph there. So let's try something other than 0. Something on the right side. How about 1/2? 1/2? What's 1 divided by 1/2? So anytime you have 1 over a fraction, you flip the fraction up. It becomes a 2. Look, 1 divided by 1/2 is the same as saying 1 divided by 1/2, which is the same as saying 1 times the reciprocal. Remember, division is multiplication of the reciprocal. So 1 divided by 1/2 is the same as that. 1 divided by 1/2, which means 1 times the reciprocal of 1/2, which is 2. So 1 times 2 is 2. So 1 over 1/2 is 2. Is that all right? Let's get even closer to 0. How about 1/4? Isn't that even closer to 0? What would happen if I plug in 1/4? 1 over 1/4 is a 4. Can I get closer to 0? Okay, give me something even closer. 1/10. Where would I be at 1/10? 1 over a 10th is 10. Can I get even closer than a 10th? 1/1,000,000th, right? Or something like that? Let's do 1/100th. That would be 1 over 1/100th, which is 100. What is happening? As I try and get closer to 0, what's happening to my function? It's getting huge, right? It's exploding. That's the common. We actually say that a lot in math with functions like this. We say that they are, well, I won't say it because I know where the minds of some people in this class will go. So I'm just going to hold that off. Okay, let's go to 1/2 and go up to 2, right? And at 1/4, we were up at 4. But it never touches. So you can never be at 0, but can't you always get closer and closer to 0? Right? Like if I say, hey, look, let's say that the wall over there is the y-axis and the floor is the x-axis. And I say, hey, I'm standing here at 1. I can always go halfway, right? And then halfway again, and then halfway again, and then halfway again. I can do that forever and never touch the wall. So I can always get closer. So my graph is going to start to do this. It's going to turn up like this. Oh, that's not a very good turn. It's going to start turning up, turning up, turning up, getting closer and closer and closer, never touching, getting higher and higher. So there's an arrow, and guess what? Another dotted line. This time I'll do it in blue. See that? Now, what do you think is going to happen on the left side? Same thing, but down. And you can check it, because if you plug in -1/2, you'll wind up with -2. -1/4, you'll wind up with -4. -1/10, you'll get -10. Does that make sense? Okay, so the graph is going to dive down over here. And then my dotted line straight up and down. Do we have on this graph any X intercepts? Does our graph ever touch the x-axis? No, it does not. Does it touch the y-axis? No. That does not mean you'll never have x-intercepts, right? Because you will sometimes have x-intercepts, and sometimes it will cross the y-axis. Every problem is unique. What I want you to gather from this first example are some behaviors of rational functions that are very important. And now I'm going to start labeling them with the definition of what we call them. So let's look again at the left and right-hand behavior. The left side got closer and closer to the x-axis. The right side got closer and closer to the x-axis. We call this horizontal dotted line that goes across. In this problem, it's the x-axis, right? We call that the horizontal asymptote. Horizontal asymptote. It's a weird spelling. If you say it real fast, people don't really care if you're mispronouncing it. Just say horizontal asymptote real quick. Now, I will abbreviate this HA from now on. What do you think we call the one here?
The vertical.
Vertical asymptote. Now, below these, I want to describe them a little bit, just kind of in layman's terms, like trying to, explain to somebody who doesn't do a lot of math what these are. The vertical asymptote, I want you to look at it, the vertical asymptote, as a barrier. This is a barrier. It forces your function up or down, right? I mean, really, I want you to see it this way. Imagine that you're riding along this function, right? Moving along. And then here comes this vertical barrier, right? It's like this imaginary force field, and you can't cross it. So when you get to it, it's like, you got to go somewhere, so you dive down, right? It forces you down. On this side, it forces you up, right? That's what it is. It's this thing you can't see, and it's like, you got to go somewhere. Now, sometimes a function will actually go up on this side and up on that side. So determining whether or not you're going to go up or down when you hit that barrier, we will have to work on later. We'll have a way of doing it. But for now, anytime you have a vertical asymptote, just know that your function is going to be forced up or down on both sides of it. Okay? Yes? Now, the horizontal asymptote is not a barrier. It does not act like a barrier. All it does is tells you what's happening at the ends. Okay? So remember with our polynomial functions, we had the left-right behavior, but we didn't know what was happening in the middle. This dotted line and that one over there do not tell you anything about the middle. They only tell you about what happens out here. So the way I've always described it is to look at this horizontal asymptote almost like a magnet that pulls the graph toward it at the ends only. You'll also notice, I hope you notice, that dotted line, the dotted line I drew, the horizontal asymptote, I only drew it out at the ends, didn't I? I did not extend the line all the way through my graph. If you go to the tutoring lab, there's a lot of tutors that will extend it all the way through the graph. I do not recommend you do that, because it may turn out that you do have your function that may, come down and cross and go back up in the middle. And if you have a dotted line going all the way through, you're going to think, what do I do? That's in my way. So the horizontal asymptote will only be telling you about what the function does at the ends. All right, we okay? All right. Let's move on. We've only done 2 problems today. 3. This is the 3rd. All right, let's look at this one. F of x equals x over 1 minus x. Is that a polynomial function? Yes? And let's try and just do a graph with the t-table. Now, trust me, the t-table is not the way we're going to be doing this. It's just to get us to get a feel for what's happening. Tell me, first of all, if you can, where is this rational function undefined, if it even is? mean, is this rational function ever undefined? Is there a number I can't plug in because I'll get division by 0? 1, right? So let's start with 1. If I plug in 1, I get 1 over 1 minus 1. That's 1 over 0. That's undefined. So guess what I'm going to have at 1? A vertical asymptote. Just like we did in the last one. Remember we had a vertical asymptote at 0? That vertical line? That's the same thing. So I'm gonna actually come over here to my graph right now, and I'm going to go out to 1. Right there's 1. And I'm going to draw a dotted line all the way up and down. This is a vertical asymptote. Now I did it in blue and I did it dotted because it's not part of my graph. Like my graph is not that dotted line. It's going to be, I'll do it in a different color, all right? So I know that much so far. Let's try some other points. We never plugged in 0, did we? Like we just started with 1 because that's what made it undefined. Let's go ahead and try 0. Does 0 work? You get 0 over 1 minus 0. That's 0 over 1. Can you do 0 over 1? Yes, that's just 0. So that means I actually have a point on my graph that lives where? On 0, 0. I'm going to do it in red. So that red dot lives on my graph. With me? Let's try some other points. What would be another point to go for here? 2, okay. Does 2 work? 2 over 2 minus 1. No, sorry, 1 minus 2. Agreed? What's that? Negative 2? Right, because that's 2 over negative 1, negative 2. So at 2, I'm at negative 1. No, wait, sorry. At 2, I'm at negative 2. 1, 2. I'll put a dot down here. Does everyone follow what I'm doing? Let's try 3. 3 over 1 minus 3 is what? Negative 3 over 2. As a decimal, that's negative 1.5. So at 3, I'm at negative 1.5. Everyone still with me? Oh, the function right here. I'm just plugging 2 into that.
Oh, you're just going to plug 2 in.
Yep, just plugging in 2. So let's try 4. All right, 4 would be 4 over 1 minus 4, which is 4 over negative 3. And as a decimal, that's about approximately negative 1.33. So I have another point over here. It's like this. You get the idea? You got, I mean, the rough idea. Like I said, this is not the way we're going to graph them, but we're trying to just see what sorts of behavior these things have. Now, my graph appears to be curving like this, right? Curving. What do I know has to happen here at this dotted line? If I'm trying to travel along my function, what has to happen there? That vertical asymptote I said was a barrier, and it forces your graph to go up or down, right? What does it look like is going to happen? It looks like it's going to go down, right? Doesn't it? But somebody tell me, well, you know what? It's not time for that. So let me fill this in. I think it's going to do this. I think it's going to come like this, and I think it's going to dive down like this because that barrier is going to force me down. What does it look like is happening as I go to the right? It looks like it's getting closer to the x-axis, right? Because what's happening as I moved to the right, like at 2, 3, and 4. Started out at -2, then it went to -1.5, then -1.33. Maybe it's getting closer to 0. So let me check it by plugging in a number that's way out there. How about 100? What would 100 over 1 minus 100 be? 100 over -99, which is negative what? So you might have to do this on your calculator. 100 divided by -99, -1.01. Well, look at that. All the way out at 100, I'm still down at -1, right? I'm not getting closer. I mean, I am getting closer to 0, but it doesn't look like I'm getting closer to 0. It looks more like I'm getting closer to what? -1. And if you try going out to 1,000, you go 1,000 over 1 minus 1,000. It's 1,000 divided by 999. You get 1.001 negative.
The one in the denominator makes it, that's like your x-axis, or your x-axis.
I'll tell you. We're going to have a way of getting it, a systematic way. But here's what I'm going to do. At -1, it looks like my horizontal asymptote isn't up at the x-axis. It actually looks like it's at -1. And it looks like my graph is actually getting closer to that. You see that? Now, you wouldn't know that. I'm just showing you, like, this is what it looks like is happening. Looks like it's doing this instead of up here. Now, we could plug some points in on the other side now also to figure out what's happening. Like, I'd really like to know what's happening in here. I know my graph has to go up or down, right? As I come in from the left side, like this, it's going to have to go up or down. If I have a point in there somewhere and plug it in, I should be able to determine if it was up or down. So let's plug in something like a half. What's 1/2 over 1 minus a half? Isn't that 1/2 over a half? And what's a half over a half? 1. So that means at a half, I'm up at 1, so I'm up here. That makes sense? So I plug, now I can pretty much say, hey, it looks like it's doing this. Now, how could I figure out what's happening as I go further to the left? Plug in some other values, right? Plug in -1, plug in -2, plug in -3. What you're going to see is this, and I'm not going to do it, okay? Because we're going to have a systematic approach. If I go -1 on the right side, or on the left side, just like I did on the right, this graph on the left side gets pulled like a magnet down towards it like this. Almost. Almost, yeah. And this is kind of similar to what we had last time, right? Kind of. It's going up on one side, down on the other. We do have horizontal asymptotes. We have something else in this problem that we didn't have in the last problem, though. What do we have? It's shifted. We actually have an X intercept, don't we? And a Y intercept. The same. It's the X intercept is the Y intercept also. All right, so the characteristics of these things are as follows. Rational functions may or may not have vertical asymptotes. You may have one, you might have more than one. They may or may not have horizontal asymptotes, but if you have one, you'll only have one. So if there's a magnet, there's only one magnet, this way. X intercepts, you may or may not have them. You may have one, you may have more than one. Okay? So there's a lot of different things that could happen here. So I'd like to give you the procedure on how to find each of these things. And then after I give you the procedure, we'll maybe take a look back at these two real quick. We have 10 minutes, so next class we'll really hit this hard. So here's our first how to sketch rational functions. All right, here we go. So I'm doing this a little different than I did polynomials. With polynomials, we came up with the steps at the very end, right? And we just kind of wrote them down. Now, with these, I'm going to show you the steps first, then we'll use them. The first thing you're going to want to do with the rational function, right, the first step, first thing, is to factor the numerator and the denominator. You'll see why as we proceed. Second step, cancel any common factors. These create holes in your graph. Now, we have not seen this, so just write it down. We'll get to it next class. All right. So the first two steps, yeah, I'm not going to move. Yeah, holes in your holes. That doesn't sound fun. Holes in your graph. Yeah, I know. These create holes in your graph. So far what I've shown you really has nothing to do with what I've talked about today. But now let's get into the things that were on our graphs. Let's start with X intercepts. The next thing you'll do is find X intercepts. Now here is how you find X intercepts. To find the X intercepts, all you have to do is set the numerator, can't spell, equal to 0 and solve. So that's how you're going to determine where the x-intercepts are. And that will always be the case. Wherever the numerator is 0 is where you're going to have x-intercepts. For the fourth step, you're going to find the vertical asymptotes. The vertical asymptotes are those vertical barriers that force your function up or down on the sides, right? As you come in from the left and right. Now, here's how to find them. You set the denominator equal to 0 and solve. Because wherever the denominator is 0, your function is undefined, isn't it? And so that's where you're going to have these vertical asymptotes. Now, finding the horizontal asymptotes is the most confusing part when you first see it. But you'll catch on to it, hopefully. Finding the horizontal asymptotes, what you'll do is this. Step A. Find the degree of numerator and denominator. You know what I mean by degree? The numerator and denominator are polynomials, right? The top and bottom. So they each have a degree to them, don't they? Degree is the highest power of x. And so the first thing you do is just identify what they are. The second step is to compare them. I'm going to call them n and d. So the degree of the numerator, is it all right if I call it n for numerator? And d will be denominator? Make sense? Okay, compare those two things. Case 1. If the numerator's degree is smaller than the denominator's degree, so if the power on top is smaller than the power on the bottom, y equals 0, which is the x-axis. Right? Y equals 0 is a horizontal line. Y equals 0. That's the x-axis. That's your horizontal asymptote. Case 2. The numerator's power is bigger than denominator's power. That means the power on top is bigger than the one on the bottom. If that happens, you have no horizontal asymptotes. That means you don't have any. You don't have a magnet that pulls your function down at the edges. It does not exist. And so what that tells you is this. The left side's going to have to go up, or it could possibly go down, and we don't know yet which one it is. And the right side is going to have to go up or down, and we won't know what it is. So in other words, if the degree of the numerator is bigger than denominator, it's almost going to act like a polynomial on the edges. It's going to go up or down on the left, we don't know which way, or up or down on the right. And what do you think the last case is? If they're the same. Case 3, if n equals d, I'm out of room here, then y equals LC num over LC den. What the heck is that? Yes, that's right. So if you have the same power on top and bottom, then what you do is you take the leading coefficient of the numerator, that's the number in front of the highest power of x, and divide it by the leading coefficient of the denominator. Whatever number that is, that's your horizontal asymptote. Okay, I'm going to run out of time, but I just want to, let's just look at this. We're not done with the steps. We still have a lot more as far as steps are concerned, okay? But let me show you just off of the problem we just did, since you have that written down. Let's just look back at this one right here. F of x equals x over 1 minus x. Okay, first step, factor. Is the numerator and denominator factored? Yes. So step 1 is good. 2, cancel any factors. That doesn't apply, right? You can't do anything? Does not apply. Or you could say not applicable. How about that? NA. Right? You can't cancel any common factors. What's the next step? X intercepts. How do you find X intercepts? Set the top equal to 0. That's 0, isn't it? I should have an X intercept at 0. Fourth step. Find the vertical asymptotes, right? How do you find vertical asymptotes? Set denominator equal to 0. Can you solve that equation? Add x to both sides. 1 is equal to x. That's my vertical asymptote. With me? Fifth step. Find the horizontal asymptote. How do you find the horizontal asymptote? Look at the degree of the top. What's the degree of the numerator? 1. What's the degree of the denominator? 1. Those degrees are the same, right? We are in case 3. That means I need to take the leading coefficient of the top. What's the leading coefficient of the top? 1. Be careful. What's the leading coefficient of the bottom? -1. What's 1 divided by -1? -1. Now let me go back to our graph. I know I'm out of time. Let me just go back to my graph and let's show you that everything that we had there is there. We have the x-intercept of 0. We have the vertical asymptote at 1. We have the horizontal asymptote at -1. It's all there. Okay? This is where we'll pick up. Remember, check your email later today because I will email the homework assignment. It will only cover polynomial functions. Have a good day.